In this video, we are going to record 7 exercises given at the end of the presentation of sampling distribution. Uh, Example, exercise 1, exercise 2, and exercise 7. So these are the 7 exercises, and we are going to solve these 7 exercises here in this recording. This is exercise 1. In this exercise, FPC is to be computed for the different values of sample size and the population size. In part A, the sample size is 2 and the population size is 5. And in part B, the sample size increases as well as the population size is 2. Now n is equal to 40 in part C and capital N is equal to 10,000. I am going to solve the FPC here. The formula of FPC is FPC is equal to n minus n divided by n minus 1. This is FPC. And where this FPC is used, all of you are already familiar that FPC is a part of variance of the sampling distribution of mean whenever the sampling was done by the help of without replacement. So it was sigma square upon n and n minus n upon n minus 1. Achha, if we take this factor, which is FPC 1, it will be 1 whenever the sampling was done by with replacement. If the sampling was done by without replacement, then this factor exists. So what we want to prove here in this in this exercise, we want to prove that as the population size increases, the FPC becomes 1. If FPC becomes 1, then the variance of the sampling distribution of mean will be equal to sigma square upon n. So this is the part that we are going to discuss here in this problem, in this exercise. For completing the different values of the FPC, I am using Excel. I am inserting the Excel sheet here in the OneNote, a new Excel sheet. This is the Excel sheet that is to be used here for the calculation of F. In one column, we have to write down the values of population size, capital N. In the next column, we have the sample size, small n. And in the last column, I am computing FPC. The first value for part A, I'm inserting one more column here in which we are referring the which part we are calculating. Part A, part B, part C. In part A, the population size is 5 and the sample size is 2. In part B, the population size is 1000 and the sample size is 10. And in the last part, we have a population of 10,000 and the sample size of 40. Now in the next column, which is the column of the FPC, we have to put the formula of the FPC. The formula of FPC is what is equal to n minus n. It is 5 minus 2 divided by n minus 1. It is capital N minus 1. This is the formula of FPC. In B2, we have the value of population size, and in C2, we have the value of sample size. The population size minus the sample size divided by the population size minus 1. This is the value of the FPC, and in part 1, it is 0.75. In part 2, it is 0.99, and in part C, it is 1. So what conclusion we are taking here for the different values of the FPC? The conclusion is that as the population size increases, the value of the FPC become closer and closer to the 1, and the effect of the entire thing is what? The effect is the FPC value will be neglected for a large population size. For a large population size, we can have the in two terms we have a large population size. In one term, whenever the actual value of n is very high, the population size will be assumed as a very large population. If the sampling is done with the help of with replacement, then a small population will be assumed as a large population. The reason is what? The reason is for a large population, uh, whenever the sampling is done by with replacement, the performance of the population is treated as a infinite population. The reason is, suppose in a bag we have only 3 balls, and we are drawing 50 balls from this population with the help of with replacement. So we can do that. If we draw a ball from the bag and replace the ball to the container before selecting the next ball, so in this way we can do the 50 selections out of a population of 3, size 3. So in a case where the population is limited, but the sampling is done by with replacement, in the both cases, the FPC value of FPC is 1, and we can say that the function of FPC will be neglected from the formula of the variance of the sampling distribution of mean. So for a large sample size, we can say that the value of FPC the value of FPC will be 1, and the variance of distribution of mean will be equal to sigma square upon n. FPC, the value of FPC is 1. This is in case of with replacement, sampling with replacement, and this is the case of without replacement. This is the case of without replacement. In case of without replacement, we have FPC in the formula. In case of with replacement, it is assumed to be 1. In exercise 2, a population is given to us. We have to determine the standard deviation for the sampling distribution of mean for a sample size of 4 by without replacement. And then in part B, we have to find out the probability that between what two numbers the probability is at least 3 by 4. So firstly, we have to check the solution of part B is basically depending on the part A. If the population given in part A is normal, then we can use empirical rule to find out either we can use the empirical rule to find out this probability, or we can use the standard normal variate and the standard normal table to find out this probability. But whenever we are doing by without replacement and the population is not normal, then we cannot say that the sampling distribution of mean will be normal. That is why we cannot use the empirical rule. Or we can take the advantage of Chebyshev inequality, because 75% observation in a Chebyshev inequality will lie between mean plus minus 2 standard deviation. So according to that, we have to determine the mean and variance of the population, and then with the help of the mean and variance of the population, we can determine the mean and variance of the sampling distribution of mean by without replacement. Then finally, according to the Chebyshev rule, we can determine the mean minus 2 sigma, the value of mean minus 2 sigma, and the value of the mean plus 2 sigma. In between the mean minus plus 2 sigma, the 75% observations will lie in case whenever the population is not normal. So this is the way to solve this problem. And now we are going to first check whether this population is normal or symmetrical or not. Uh, Firstly, we will making a frequency table for the population. Unique values are to be noted in column number 1, and their frequencies will be in column number 2, then 5, 6, and 7. These are the different values of the population. I am representing the population by capital X and font size increasing. Now the frequencies are computed. Frequency of 1 is 3, and the frequency of 3 is 1, and the frequency of 4 is 1, and the frequency of 5 is 1, and the frequency of 6 is 3, and the frequency of uh, 7 is 1. So by these frequencies, we can clearly see that the population is neither symmetrical nor it is bell-shaped. So we can take the decision of the theorem. Okay, if the population is not normal and the sample size is small, we cannot say anything about the size of um, shape of the sampling distribution of mean. So in this case, we cannot take a decision that the sampling distribution of mean will be approximately normal, because neither the population is normal nor the sample size is large. Therefore, the advantage of central limit theorem we cannot take here. So we have to calculate the values of mean and standard deviation of the sampling distribution of mean. And after that, we are taking the decision of Chebyshev inequality, because the population, if the population is not normal, we cannot use the empirical rule to solve it. So for computing the mean and variance of the population, I am making the few more columns here. We are making the probabilities by relative frequency 3 by 10. It is 0.3, 1 by 10, it is 0.1, it is 0.1, it is 0.1, it is 0.3, and it is 0.1. The sum of all probabilities must be equal to 1. You can see the total is 1. Now for computing the mean of the population and the variance of population, I have to make the two more columns. One column is x into px, x into px, or px, and x square into px. And there is a product sign in between these two, x into px and x square into px. These two columns are required for computation of mean and variance of the sampling distribution. Not sampling distribution, mean and variance of population. X into px and x square into px. X square can be written as 2 and a subscript superscript x square into px. These two columns I am constructing for computing the mean and variance of the population. Here we have to plug the formula. Formula is x multiplied by px, and this is to be used next. Now x square, which is the square of this, multiply by px. Px is this. So you can see the formula of x square times px. And then I will use to calculate the sum of these two columns. Sum is quite simple, the sum of this and the sum of this. Now we have the two columns we have. One is known as the x times px, which is the mean of the sampling distribution of mean, and this is the variance of the sampling distribution of mean. And now mean of the population mean of the sampling distribution of mean, it is equal to the population mean. The first theorem is, and my population mean is 4. Second theorem is variance of the sampling distribution of mean. Variance of the sampling distribution of mean is equal to sigma square divided by n and the FPC. Now the value of sigma square, we have to calculate the value of sigma square here, because this 21 is not the variance of population. We have to compute the variance of population by a formula that is in Excel. The formula of the variance is summation of x square time px, which is 21, minus the square of summation of x into px, which is 4 square. The 4 square is 16. So the variance of the population is 5. So now we have the value of the population variance as well as the mean of the population. Mean of population, it is 4. Now the computation of the sampling mean and variance of the sampling distribution of mean will be take place. This is equal to 5 divided by sample size 4, multiply by the FPC. FPC is the population size. We have the 10 observations in my population, minus the sample size is 4, divided by 10 minus 1. And the answer will be 15 upon 18. Now we have the mean of the sampling distribution of mean and the variance of the sampling distribution of mean. Now, according to the Chebyshev rule, we are going to calculate the two values. One value is x bar minus mean minus 2 times of the variance of the sampling distribution mean, and the second thing is mean plus 2 times the standard deviation of the sampling distribution of mean. So this can be written as probability of mean minus 2 sigma x bar and in between that we have what? We have x bar, which is the sampling distribution mean, and it is equal to mean minus plus mean plus 2 sigma x bar. This, according to the Chebyshev rule, it is 0.75. It is greater than or equal to 0.75. So the question was, in between what two numbers we have at least 75% observation will lie within that. So these two numbers we have to compute here. That is mean minus 2 sigma x bar. This is the first value of the interval, which is the lower limit. And the second thing is mean plus 2 times of standard deviation of mean. Mean minus 2 sigma and mean plus 2 sigma. The sigma is not the sigma of population. The sigma is the standard deviation of the sampling distribution of mean. Now the population mean is 4 and population variance is 15 upon 18 and the standard deviation will be under root 15 upon 18. So we have to put 4 minus 2 times under the root 15 upon 18. This is the lower limit of the interval and this is equal to 4 plus 2 times under the root 15 upon 18. The results of these two are to be, it is equal to 4 minus 2 times, and the value of under the root 15 upon 18 is 0.912871. 0.912871. And then this number is 4 plus 2 times 0.91. This is decimal point here. 0.912871. The answer of lower limit is 2.174 and the answer of upper limit is 5.825. So now we can say that in between 2.174 and 5.825, we have at least 75% observation of mean will lie between these two numbers. This is the end of this.